Hello and welcome to the final video demonstration of the course project for IDS 576 in fall 2019 by Team 2. Today I'm going to be walking you through both the report that we put together and the code for our project. And we will first start off with the report and give you a little background about the motivations for this project and the structure of the paper, the results, and then we'll move on to the code and actually see how we arrived to the results that we have. And this research was originally started in the summer of 2019 with Professor Teja. Um, I Jasur personally started working with him, and then once this course started, we continued it and changed the direction a little bit, but we were still able to accomplish plenty with this project. So let's start. The title that we gave to our project or paper is Marketing Campaign Simulator to Model User Behavior and Optimize Offerings. So in summary, what we're trying to achieve here is using some of the algorithms and techniques from the RL reinforcement learning family. We would like to put together a marketing simulator that offers campaigns to customers. Um, but the unique thing about the simulator is that it incorporates some of the user biases and behavior. So that is the gist of what we have done here. So the paper, as you can see on this section, is divided into multiple sections: introduction, and then we'll give an overview for behavioral economics, and then we will give you an overview and background about reinforcement learning, graph modeling, and we will describe the framework we used for the simulator, and we will describe our results, conclusions. And we have plenty of subsections here, and I'm going to be walking you through all of those first. So introduction, I mean, this paper will be provided as part of the deliverable, so we're not going to really go into all the details of it, but basically what we have here is why we were inspired by reinforcement learning and the intersection of it with marketing. So we were inspired by two things: reinforcement learning, recommender systems, or any kind of simulation that models user behavior, and also behavioral economics research. And putting that two together, we came up with an idea where what we said was if we had, based on the well-researched biases, heuristics, and tendencies, if we were to put together a simulator that kind of incorporates those biases that people have while making a marketing decision. So imagine you get a marketing offer, and if there's if the simulator makes you a marketing offer, but it also has certain assumptions and probability distributions with regards to how you might act in certain situations, and if it's pre-coded, then we wanted to see if that simulator can optimize the offerings in that kind of environment. So that was the main motivation. And here we actually describe in this section the behavioral economics and what it is and how it came about. And the four subsections here that we have actually go into detail with regards to the specific biases and heuristics, what we generally call as user behavior components. So first one is the status quo bias. We give a little background, but in short, it is basically the people's tendencies to stick with what they already know. And in the context of marketing, it applies to brands and products that they are already familiar with. And the second one is loss aversion. Loss aversion basically meaning it's losses have much greater impact on preferences compared to the gains. So first, here we have, for instance, if a person was presented with a choice to either gain $100 or avoid losing $100, people generally prefer the latter. So in the context of marketing or in our simulation, what we have done is um, if we have a message in the offer, it says, hurry, this offer is valid until the end of the day, it seems very urgent. So the feeling of missing out, or FOMO, the fear of missing out on the discount, even if it means that they have to spend money on it now, is greater than actually not getting it. So that they're loss averse. There's hyperbolic discounting, meaning that the gains currently are valued or perceived higher gains at a later date. So if somebody can have $50 now compared to $200 in 10 months, most people would prefer the former. Here I have highlighted it. So that has been shown in research, and what we have done here is we incorporated that as a we defined the intrinsic value of a marketing offer. So it contains both the immediacy of the offer, the availability of the offer now, and also dollar amount as discounts perceived value. And I'm going to be going into details about how we structured all of those. Just giving you a little background here now. And then there's mental accounting. The concept of mental accounting is basically money. People don't always treat the money as fungible, meaning that the same amount of money dedicated for one thing is not as the same as the same amount of money dedicated for another thing. So mental accounting plays a big role, especially in budgeting. So people tend to have a variety of mental accounts for gas, groceries, or equipment and things of that nature. And then we give a little background about reinforcement learning. I mean, we covered that in class, so there's no need to go into detail, but basically we described the environment here, what is the structure of reinforcement learning, and what is the basic, how it basically operates in a very fundamental level. And then we described the difference of reinforcement learning from supervised learning here, based on some research that we have done and literature review. And then what we have done is, in the RL or overall online learning families, there is confidence bound UCB algorithm. So we use that UCB algorithm to actually optimize our offerings. And here we provided kind of a business scenario similar to ours, being motivated by the multi-armed bandits problem, and then we have the mathematical and statistical structure of how UCB algorithm sequentially makes decisions. So we describe all of this here, and then we give a quick introduction to graph modeling, or how basically we were connecting all of our probability distributions across actions and states in our model through a belief network or a Bayes network. And then finally here we actually go into detail about how our simulator operates. So the simulator, let me give you a little overview. The simulator is a marketing campaign simulator that makes offers to people. And then actions is marketing actions taken by the simulator. So we have possible action families are 4, and number of actions are 11, but possible action families are 4. So they can 11 actions can fall into one of the 4 categories. So it's message, time, brand, and discount value. Message can be urgent, medium, or not urgent. Time can be now, near future, and distant future. Brand can be new or the same, and discount value can be less than the mental account, greater than the mental account, or equal to the mental account. So if it's less than the mental account, it basically signifies that if I was planning to if I was planning on spending about $80 on a particular item, and I am presented with an offer to buy it for $50, that's less than what I was budgeting it for. So, and then we have user behavior, otherwise known as states or maybe biases. So user states and biases are simulator makes after a simulator makes them a marketing offer, we basically code how they might potentially feel. So loss aversion, hyperbolic discounting are the two. So serious, somewhat serious, not serious is loss aversion, and hyperbolic discounting, this is discounts perceived value. So it's affected by time. So if I make somebody an offer currently right now, then they potentially perceive that discount's value as very high. We have the response, users either accept or reject the offer, and we have the customer profiles. We'll be going into that later, but I'm going to be skipping to the next section, which is the Bayesian networks. So here, as you can read through this, but we have the probability distributions for all of our actions. So here, actions and states. So message affects loss aversion, time affects hyperbolic discounting, and we have the mental account or status quo, either otherwise known as brand, affecting response. So we have coded all of these here, but in addition to this, we actually developed customer profiles, meaning so this Bayesian network that we described in the section number 5, I believe, is a part of what we call general customer that incorporates a little bias from everything. And then there's reactive customer. They have high loss aversion, high hyperbolic discounting. So I'm not going to give a description as for each customer profile, but in short, we have 5, and they all have certain characteristics or tendencies that they're more inclined to be biased towards one or the other. And what we wanted to do through this is actually see how the algorithm or the simulator will change its course of action for each customer profile. So now, before moving on to the results, I'll show you a little bit of the code. So we have the setup here. We coded actions and states as dictionaries, and also the response. We coded all of our environment components as dictionaries, and then we have so here we made custom functions that actually basically code what we have in the Bayesian network that we showed earlier. But remember, this is the original model. Most of these are. And then we have the response. So how all of these that I showed here that are deciding whether or not the customer will accept or reject the offer interact with each other here. So we have the probability distributions. But also what's interesting is, and what's really useful is, we actually changed some of those, or at least created new probability distributions for some of those depending on the customer profile that I just described. And you can read through the descriptions and look at the probability distributions, and it should be able to make sense. And we have this long function that goes through each one of the combinations and actually decides whether or not or to what extent the customer is likely to respond. Then we generate data. So we generate 1 million records, and we generate actions. And actions also have probability distributions here, but when we're coding it in the data frame, and a data frame called env environment, we actually can specify the probability distribution here depending on the customer profile. So this is general model, this is reactive customer, this is budget cautious customer, for example. So we have different probability distributions for actions for all of those. And we have the user behavior, and the functions here stay the same because the distributions are from here. So if we change the distributions here, then all we have to do is just rerun the code. Then for user behavior, we just generate data here with the responses, and then this is just taking a quick look at the code and what it is generating. And then what's one of the important points that I actually missed here is, here's how our structure or algorithm operates. So we have a simulator here. We generate actions, and they affect user behavior. So here we are generating actions here, as named here. We're generating actions, data generation actions, and then they're impacting user behavior. And user behavior will ultimately trigger the response. And we will take the responses and sample that data, 1 million, and sample, let's say, 40% of it, and we then feed it into upper confidence bound algorithm. So we have a little EDA section here, but that's not vital as of now. It's just for our own learning. And then we have the UCB algorithm part here. So we basically load the data after cleaning it. So the data structure here is, we did a little bit of cleaning in the earlier sections over here, cleaning for output, but basically I'll explain what it is doing. So in each section, these are all the possible 11 actions, and what it means is, for customer ID number 0, let's say, a not urgent marketing offer was sent, and it had a message that was not urgent, and discount was available in distant future, and status quo that was shown was basically a new brand was shown, and then it was greater than what they were planning on spending. And all the ones here indicate that the customer has responded. So the customer responded to an offer with all these 4 characteristics. That's what it means. The encodings here, that's what it signifies. And then we randomly select a random selection section here, basically randomly selecting actions and seeing how they perform. So on that 400,000 sample, we sampled 40% of the data. We got in total 123K responses. So that's not terrible, but let's see if we can do better with the UCB algorithm. So we have the UCB structure here, and what we did was basically then print the number of um, responses that UCB has received, and that was 170K, so it increased. But the distribution we can see here is most of it is coming from one action. So let's see what action that is. It's index number 6. Let's try to visualize that here. So that's status quo showing new. So if a new brand was shown in this particular sample, then the click-through probability was about 42%, but it was shown almost exclusively. So that is just for the general customer profile in one random sampling. But basically, we have in the results section, we have results for all of our customer profiles. We have the general customer, reactive customer, budget cautious customer, and we kind of provided the response rates, click-through probabilities per action, and then on the insight section over here, we actually wrote up a thorough overview of what those are doing. But just to clear up some of the important points here, we are generating um, we are generating random data, and that is one of the limitations that we discussed in the limitation sections later. We're generating data with action probabilities, and these vary based on customer profile. And those actions will eventually impact the user behavior, their biases and heuristics, and how they're going to make decision. So it comes to response. Once we obtain the responses for 1 million customers, then we sample that data randomly and feed it into UCB algorithm and see how we can exploit certain actions more, because we all know that it is very costly, as we discuss over here. For example, one of the most fundamental business assumptions about our framework, that it is very costly to send a marketing offer with all of the characteristics that normally lead to a faster conversion. So if we send an offer with an urgent message available currently, and it is from the same brand that has a very big discount value, from a business standpoint, this is not a very efficient or effective long-term strategy to follow. So instead, what we're doing is, once we sample that simulated data, we for example, we saw here that, not urgent message and distant future, so all of that led to one conversion, all these characteristics. But what we're doing is, or send an offer at least with less characteristics that still lead to that conversion, and what that action is, what that characteristic is, and can we exploit that? So here it's more or less equally distributed apart from one, but here, as we can see, we're really exploiting, but the number of total rewards we're getting has increased significantly. Um, so that is the gist of our project, but the full details are on the paper as well as on the code, and we have all of the scientific references that we used here. And then just finally, limitations and areas of improvement. First, we need to have real-time data for this to really improve this, because this is still a simulated data. We have to include additional biases. We covered some of the fundamental ones, but there's still plenty of documented ones to follow. We have to use more advanced algorithms, like classic ones like Q-learning, or more advanced techniques like deep reinforcement learning, or LSTMs, because currently our model is stateless, meaning it is one transactional. If the same customer comes back again with the same biases, the strategy will be reset to new and then will be followed again, instead of actually customizing or being more proactive with that same customer. And finally, because we can be adding more biases, and we can be using more advanced algorithms, there's a possibility to do value function approximation. We represented our action state in action state space and Bayesian network in a tabular form. But as we increase the number of actions and states and their relationship, it becomes enormous and it's very hard to follow. So in that case, we want a more compact function that represents the network and generalizes across everything really well. So we can use the function approximation. But as the results section show, as you can read through, we obtained pretty impressive results, especially for each customer profile. And we believe that there is a that's a strong indication that we're on the right path, and this can be researched further and developed even more. So you can take a look at the code. It will be provided as part of deliverables. And that's it for me for now. Thanks so much.